Hi guys, we've been working all through Chapter 7 on similar polygons, similar figures, and I decided to combine this Section 5 up in Chapter 11 into our Chapter 7 study. The topic of this section is areas of similar figures, and it just makes sense to combine it into similarity. So in this section, we're going to find the areas of similar figures when we know the scale factor, and we're going to go in reverse and find the scale factor or missing sides of polygons if we know the areas of similar figures. Okay, let's look at a key theorem here, the area of similar polygons. The theorem states that if two polygons are similar, then the areas are proportional to the square of that scale factor. Kind of think of it this way. If you look at the area of any polygon, that will be in square units, square inches, square feet, square centimeters. So think of it as that ratio being also square to the scale factor. The easiest way to prove this would be looking at squares themselves. So I have a square ABCD. I'm going to mark all the sides congruent. So each side, say, will be S in length, and then the area of ABCD is going to equal side times side, or side squared. Now let's look at a proportional or similar square, EFGH, over here. And if they are similar, then I've got some kind of scale factor multiplying ABCD side length. So all of these sides are going to be KS. Consequently, the area here of EFGH is going to equal KS times KS. And that equals K squared times S squared. So then if we look at the area here of EFGH over the area of ABCD, we've got K squared side squared over side squared, and you can see that these cancel. So if we look at the area of these similar squares, you can see that their ratios are equal to or equivalent to the scale factor squared. And it's easy to see this relationship looking at squares, but this will apply to any polygon. So you can look at a trapezoid or a triangle or a rectangle. All similar polygons, regardless of the number of sides, are going to have the same ratio where the ratios of their areas are going to equal the square of the scale factor. Okay, let's take a look at how we can apply this theorem. If ABCD is similar to PQRS and the area of ABCD is 48 square inches, find the area of PQRS. Well, I know that most of you would probably approach the problem this way. If the area here of ABCD is 48 square inches, and you have one side length of 6, then clearly the other side of the triangle has got to be 8 to obtain an area of 48. And probably the easiest thing to do over here on PQRS is to find that other side as well. So we could always do a ratio. We could say, well, let's put corresponding sides together. And the key thing on this problem is, although 8 inches is here, BC, it's actually not corresponding to RS. So don't be fooled that these two are here and that they are in corresponding position. It's key here to look over at the order of the vertices. CD is in the 3rd and 4th position, RS is in the 3rd and 4th position. So in fact, CD is corresponding to RS. So be aware of that. So we can say CD is corresponding to RS as BC is corresponding to QR. And substitute. 6 is corresponding to 9 as 8 is corresponding to X. So we can find that other side, and we can see that 6X equals 72, and therefore X equals, whoops, my pen's not working, X equals 12. Okay, so that's certainly the quickest and easiest way to find the area of PQRS, and it's easy to see here that the area is 108. However, let's try to work on the theorem itself. So if we look at the theorem states that the area of one of the polygons, ratio of that to the other, is going to equal to the square of the scale factor. So if we look at the area here of ABCD, we have 48. We're looking for the area of PQRS. And our scale factor, as we can see, is 6 to 9. So we could put that in and square it. Whoops. And we might as well simplify here first before we square. The area of PQRS equals 2/3 squared. So we've got 48 over the area of PQRS equals 4/9. And if you cross multiply and solve, you will arrive at the exact same answer we already have, which is the area of PQRS equals 108 square inches. Alright, let's take a look at another problem. EFGH is similar to LMNO, and the area of EFGH is 40 square inches. Find the area of LMNO. Okay, so we know that the area, again, of LMNO to its similar figure, EFGH, is equal to the scale factor squared. Now notice I put the larger one this time on the top. It really doesn't matter, but you just have to be consistent. So I just want to show you different ways to set up the equation here. So the area of LMNO, we don't know, we want to find. And we know that EFGH is 40 square units. And the scale factor then is going to be, since I put the larger figure on the top, I have to adjust here and put my scale factor is 12 to 4. So looking at corresponding sides here again, we've got HG or GH here in third and fourth, and NO in third and fourth. So that's our ratio. Okay, so we've got the area of LMNO over 40 equals the square, and I'm just going to convert 12 divided by 4 to 3 equals 9. Therefore, the area of LMNO when we cross multiply is 360 square feet. Taking a look at example 2, the area of ABC triangle is 98 square inches. So I'm going to write that down here. And we're told that triangle ABC is similar to RTS. Find the scale factor from ABC to RTS and the value of x. Also, the area of RTS is 50 square inches. Okay, so we know that the ratio of the areas, so area of ABC to the area of RTS, is going to equal the square of the scale factor. So let's substitute in what we know. We know 98 over 50 is the square of the scale factor. And since I put the larger triangle on the top here, I have to put a side over here from the larger triangle, 14, and that corresponds to x squared. And we can say 98 over 50 equals, if we square 14, we get 196, and square x, and we get x squared. Cross multiply 98x squared equals 50 times 196 is 9,800, I believe. And so if we solve for x squared here, divide both sides by 98, we end up with 100. And finally, we can solve for x by taking the square root of both sides, and x equals 10. And don't lose sight of the units that we're solving for, so it's going to be 10 inches. So the missing side length here, ST, equals 10 inches, and The scale factor, we were asked to find the scale factor from ABC to RTS is going to be 14 to 10 that we just solved for, and we can reduce that to 7/5. Taking a look at example 3, the area of one side of a skyscraper is 90,000 square feet. The area of one side of the scale model is 200 square inches. If the skyscraper is 720 feet tall, about how tall is the model? One of the things I don't like about this problem is that the reader has to assume that the side of a skyscraper is a rectangle, and that's not always the case. But let's call this a skyscraper. And we've got some model here of the skyscraper, and clearly I don't have this drawn to scale. We know that this is 720 feet tall, and we're being asked for this. How tall is the model? We also know that the area here of the skyscraper is 90,000 square feet, and the area here of the model is equal to 200 square inches. All right, well, the first thing I hope that you see is that we've got feet, and square inches. So we have to convert one to the other, and it really doesn't matter which way you go. I guess I'm going to choose to convert the square inches into feet. So first thing we need to do, we've got 200 square inches, and I want to convert that to square feet. I'm going to multiply that. I do know, that's inches by the way, I do know that inches are on the top here, the numerator, so if I want to get feet on the top, I need to put feet here and inches here. I know that 1 foot is 12 inches, so I've got one of my inch units canceled out, and I got to keep going because I have square inches. So down here I have now 12 times 12, or 144 square inches. Now I can start canceling. The square inches are gone. By the way, I did not finish this here. That's a foot. So my inches, inch squared divided by inch is canceled, and I now have square feet on the top. So 200 divided by 144 comes out to be approximately 100.39 square feet. So let's rewrite that here. This is about 1.39 square feet. Okay, so let's look at the ratio. The area of the skyscraper to the area of the model equals the scale factor squared. And we have the area of the skyscraper is 90,000 to the area of the model, which we now know is 1.39. And we can take a look at the scale factor. We've got 720. Since I put, again, the larger image, the skyscraper, on top, I've got to put its dimension on the top, and we don't know what the height is of the. And we just want to square this. And so if we take the square of 720 over x, we get 90,000, 1.39 equals, and the square of 720 gets to be some big numbers here. We've got, that's a 5 by the way, here let me erase that. We have 518,400 over x squared. If we cross multiply and solve for x by taking the square root, I'm running out of space here, so I'm just going to give the answer. X is approximately 2.83, and that would be feet. Okay. 3 final problems to take a look at. So number 1, 2 rectangles are similar, we're told, with a scale factor of 4 to 7. If the area of the larger rectangle is 294 square inches, find the area of the smaller rectangle. Well, I think it's always best to draw some kind of sketch. The area of the larger, and we got area of the smaller. So the larger, we've got an area of 294. And the area of the smaller, we don't know. So I've got A sub L, A sub S, don't know. And we know that the area, I'm just going to put larger on top just for convenience, to the smaller is equal to k squared. The area of the larger is 294. I'm substituting. The area of the smaller we're trying to solve for. Now be careful when you set up the scale factor. Since I just happened to put area of the larger on top on my ratio, I have to be consistent. So I am going to take the reciprocal of 4/7 and put 7 here on the numerator because I have to make sure I'm consistent. So 294 divided by the area of the smaller equals 49 over 16. If I cross multiply and solve, the area of the smaller rectangle turns out to be approximately 96, actually not approximately, I think it's actually exact, is 96 square inches. Next problem. 2 triangles are similar with a scale factor of 1 to 3. If the area of the smaller triangle is 22 square feet, find the area of the larger. Well, maybe quick draw sketch. The area of the smaller triangle is 22 square feet. And the area of, I'm going to put AS, area of the larger, we don't know. So we do know that the area ratios, I'm going to put smaller first to the larger, equals k squared. The area of the smaller, I'm going to substitute, is 22. We don't know the area of the larger. And again, we got to be super careful here with the scale factor. Since I put the smaller on the top and the larger on the bottom, we're good to go by just using 1/3 squared. So 22 over the area of the larger equals square 1/3, and that's 1/9. And if we cross multiply and solve, we get the area of the larger triangle is going to equal 198 square feet. Okay, the final problem. The ratio of the areas of 2 similar squares is 16 to 81. If the length of a side of the smaller square is 24 units, find the length of the side of a larger square. So as always, I think a little sketch is helpful. So we have a smaller square and a larger square. And we know that one side, or all sides of the smaller square, is 24 units. And we don't know what the side of the larger square is. But what we do know is that the ratio of the areas, so area of smaller to area of larger, equals the scale factor squared. And we're told that the ratio of these areas equals 16 to 81. So we can just replace this with 16 over 81 equals k squared. Now if I want to solve here for k, I'm going to take the square root of both sides, and we get 4 over 9 equals k. So now we can use that k to solve our unknown side. Now I've got the smaller unit here on top, and I've got the smaller units here, so I think we're okay. I'm going to say 4/9 equals, and the smaller side is 24, and the larger side is 9. If we cross multiply and solve, we get x equals 54 units long. Thanks for listening. Hope it helps.